So if we had a battery charger, one way you could imagine this is you might have a 12 volt, an automotive battery, a 12 volt battery, and you might have a wall outlet. So this 24 cosine theta might actually be a transformer or something like that. It's supplying 24 volts. It might have 120 over here, and 24, well, 167 is what 167 cosine theta might be what it is on this side, and 24 cosine theta on that side. So some scheme for reducing the voltage, and a resistor to limit the current that we apply to the battery. And if we had a circuit like this, why is that adding? It should be subtracting. It's pushing and go backwards. So this won't work, but let me show you why it won't work and why there's a problem. To charge a battery, we always want current going in. We're trying to supply electrons, so we want to move electrons into the battery. We don't want to lose electrons from the battery. The battery is storing electrons, of course. We want to move electrons in. And so if we use this circuit, you could see by KVL, if we've got the voltage on the source, if Vs is greater than 12 volts, then we will have current going into the battery, and it would be something like 15 minus 12 minus the drop in this resistor, ID times 100 ohms. That should all sum up to 0. That would be the voltage drop all the way around the battery, or all the way around this circuit. And what would we have? So we need to find ID. So we'll solve for that. ID is equal to 15 minus 12, or 3 volts divided by 100. That would be 30 milliamps charging. And critically, importantly, that's a positive current that we've got going in there. So that's good. We're charging. In the resistor, we would have a power dissipated in the resistor, so PR. That would be I squared R. There's a couple of ways we could find it. That would be an easy way. So 0.030 squared times 100 ohms. That gives us the power dissipated in the resistor is 0.09 watts. 90 milliwatts dissipated. Okay. And what we're really interested in is the battery, what's going into the battery. So how much power are we sending in? So again, that's now we use VI because we don't know the resistance of the battery. So we have 12 volts. That's the voltage on the battery. Oops, sorry, it's not 24 volts. That's a 12 volt battery. It could be a 24 volt battery, but we'll make it a 12 volt battery. So we've got a 12 volt battery, and that's the voltage across the battery, and we're running into it 30 milliamps. So 0.30, and that works out to 0.36 watts, or 360 milliwatts. And we're dissipating it. It's a positive sign again, so that's all good. We are charging the battery. That's exactly what we want to do. Now, but this is a sinusoid, so it's going up and down. So it's going to go negative. The power, the energy we get out of the wall does go negative. So when Vs is minus 15, those are the worst cases, the best and worst cases perhaps. When Vs, the source, is minus 15 volts, now this same KVL equation, now it works out to minus 15 minus 12 minus ID times 100 sums up to 0. Or we could say that ID is now minus 15 minus 12 over 100. And that's minus 27 over 100, or minus 0.270 amps. In the resistor, the power in the resistor, we can still use I squared R. So we've got 0.27 squared times 100. And that's 7.29 watts dissipate. We'll always dissipate power in a resistor. So that's not good. I mean, we've increased our the discharge power in the battery or the resistor from 0.9 watts all the way up to 7 watts. So we're just wasting a lot of energy making that resistor get hot. But the real problem comes in the battery. So when we look at the power in the battery, again, we have to use VI. So now we've got plus 12 volts, because that's still the voltage on the battery, right? The battery will always have 12 volts on it. I mean, it'll change gradually, but it's always going to have some kind of positive voltage. It better not have a negative voltage on it. So it's got a positive voltage. So plus 12 volts, but we've now got this negative current right there, negative 0.27 amps, so minus 0.270 amps, and that equals minus 3.24 watts, and now we're generating, right? Generating power from the battery is equal to discharging the battery, right? That's a bad thing. We're discharging out of the battery 3.24 watts in the worst case. And in the good case, when we were charging it, we were only adding 0.36 watts. So we're obviously going to quickly discharge the battery and get that resistor real hot. And we're not going to charge the battery at all with this circuit. So this is no good. That's a terrible battery charger. We need something that will limit the voltage going into the battery so that it's always positive. Even though the voltage on the battery will change over time. As it charges up, the voltage in the battery is going to go up. It's going to be 12.5, 12.6, up to close to 14 volts. It's always going to be going up, and this power supply, this AC power supply, needs to adjust and always be able to charge it. It could start as low as 3 or 4 volts, but it's going to go up. So we can do that with a diode. If we have the same circuit, we have a resistor, but now we have a diode to limit the flow of current so that we can't have any current going backwards. So we still have Vs is equal to 24 cosine theta, and we still have 100 ohms, and we still have plus or minus 12 volts. Anytime, and we can analyze this with just the very simple model, the ideal model of a diode. And remember, in that case, if the voltage in the diode is greater than 0, or the current, so it's greater or equal to 0, or the current is positive, then the diode is a short. And if we have a negative voltage, or ID is less than 0, then the diode is an open. call that off, and we call this on. So first, anytime Vs is greater than 12 volts, if the source is greater than 12 volts, the diode is on. And anytime it's less, it's off, or it's an open circuit. So the two choices, two possibilities would be Vs is greater than 12 volts, then we've got a short circuit. And it looks just like the previous real simple diode circuit, and we'll be charging. And if Vs is less than 12 volts, then we have an open, and nothing's happening. The battery just sits there, but at least it's not discharging, right? There will be no discharging. So during this time, we're charging. And here we're not doing anything. It's just hanging out. And if I try to draw sinusoidally what's happening, we've got voltage here. So we've got a sinusoidal Vs, and then we've got a limit on the battery of 12 volts. Anytime Vs is greater than 12 volts, which is, let's go in this, oops. Yep, there we go. In this region here, we're charging, right? Anytime the voltage on the source is greater than that 12 volts in the battery, we're charging. And the battery, or the that source, can go up to plus 15 volts. And minus 15 volts. Those are the limits on the battery. So what happens when we are in the other half of the situation? So in the negative half, look at white, nothing shows up. So again, we've got 12 volts. It's the battery voltage. And we've got the source that can go plus 15 and minus 15. Now, whenever we go negative, we're in this region. And nothing happens during this time. As long as the diode is turned off, it's an open circuit, and there's no discharging, so we protected it. And it'll charge at that rate that we found before of 0.36 watts. At maximum, we'll be charging it like that, but at least we'll be charging it at 0.36 watts. And during this time over here, nothing happens. We don't lose anything. So a good question is, what is the on angle, or the charging angle? So we want to know when Vs is equal to 12 volts, and that's equal to 24 cosine theta. So then we've got cosine of theta is equal to 12 over 24, where that equals 1/2, just by the numbers that are very conveniently picked here. And then theta is equal to 60 degrees. So that means that those times that 60 degrees, that's occurring at that spot right here. Well, I drew sine instead of cosine. But that's 60 degrees there. And we've got another increment of 60, 360 minus 60 right there. And the total the total conduction angle will be twice theta, or the charging angle, because there's some occurring over here and there's some occurring over here. So we'll be charging for 120 degrees out of 360 degrees, or about 1/3 of the time. So that sounds kind of silly. Sounds like a waste, but at least we are charging, right? So at least it's got this case where it is actually charging, and at the peak, let's see, I said something wrong over here. Yeah, that's not 15, it's 24, isn't it? Those peak values are not plus and minus 15, they're 24. 15 was the example I used. So let's just correct that. So it goes to a peak of 24 volts, minus 24 volts, minus 24 volts, and plus 24 volts. Those are the peaks. And at that peak, when Vs is equal to 24 volts, we could find the peak current, and that would be the diode current at the peak would be equal to 24 minus 12 over 100 ohms, or 0.12 amps charging. All right, that would be the peak current. Most of the time, the vast majority of the time, it'll be less than that, but that will be the maximum that we charge it with, just at those peaks.